99% of people believe dinosaurs were slow, cold-blooded giants. But this ancient image is rapidly being challenged by modern science. The central question, were dinosaurs ectotherms or endotherms? Ectotherms rely on external sources for body heat, like modern reptiles. Their activity levels are directly tied to the environment's temperature. But endotherms, conversely, generate internal heat through metabolism. But this allows for sustained, high-energy behaviors regardless of ambient warmth. Now that we understand X, let's explore why the fossil evidence. Bone histology provides crucial clues about growth rates. Rapid growth rings suggest high metabolic demands, characteristic of warm bloods. Reptiles show slower, more spaced-out deposition of bone material. However, some dinosaur bone structures resemble those of cold-blooded animals. This complexity suggests not all dinosaurs fit neatly into one category. Next, we examine cardiovascular evidence embedded in their anatomy. Warm-blooded animals require sophisticated vascular systems for heat regulation. Fossilized skulls sometimes show evidence of complex respiratory turbulence. But these structures efficiently cool the brain during exertion, suggesting high activity. Consider the immense energy needed just to sustain a gigantic body mass. Gigantothermy posits that sheer size could retain heat internally. This passive retention might mimic warm-blooded traits without true endothermy. The muscle attachment sites, however, suggest powerful, sustained locomotion. Active predation requires rapid reaction times, favoring higher baseline temperatures. This implies a metabolic engine running hotter than modern cold-blooded creatures. Parental care offers another fascinating window into dinosaur energy management. Modern birds, descendants of dinosaurs, often brood their eggs for warmth. Unfossilized positions suggest many dinosaurs also sat atop their developing young. But what about dinosaurs living in colder, high-latitude environments? Evidence of insulating feathers strongly implies endothermic requirements. The feathers are a significant adaptation against ambient temperature fluctuations. But only internal heat generation can maintain activity in prolonged cold. And now that we understand X, let's explore why the spectrum theory. But the concept of a metabolic spectrum is gaining wide scientific acceptance. But the smallest dinosaurs, like early theropods, were likely fully endothermic. The largest dinosaurs, however, faced a heat dissipation challenge. Their enormous internal volume kept them constantly warm, regardless of external temperature. Their surface area to volume ratio worked against losing excess heat quickly. Or they operated at high temperatures, but perhaps not through active generation. Intermediate sizes, the bulk of the dinosaur population likely fall in the middle. These animals may have been mesotherms, fluctuating within moderate ranges. This metabolic flexibility allowed dinosaurs to dominate diverse global ecosystems. Let us look at oxygen levels, a critical factor in metabolism. The Mesozoic era featured higher atmospheric oxygen concentrations than today. And this readily available fuel source supports highly active, high metabolism lifestyles. Avian lungs are extraordinarily efficient, a trait inherited from their ancestors. This efficiency suggests dinosaurs possessed active methods of oxygen processing. High metabolic rates demand powerful, four-chambered hearts like mammals and birds. Reptilian hearts often mix oxygenated and deoxygenated blood inefficiently. The active lives they led strongly argue against a purely sluggish, cold-blooded existence. Wear patterns on teeth can also hint at feeding habits and metabolism. Constant mastication of tough vegetation demands substantial energy output. The debate hinges on how we define warm-blooded in deep time. But evolution rarely offers simple binary answers. Biology exists on a continuum. At the small, feathered dinosaurs were almost certainly energetically active. The giants, however, might have utilized size to passively maintain core temperature. This mirrors the gigantothermy seen in today's largest terrestrial mammals. And the core temperature of the giants likely remains stable and high. Or sustained, long-distance movement requires consistent energy mobilization. A new analysis of cellular structures continues to refine the metabolic picture. The truth is a spectrum. Some dinosaurs burned hot, others ran warm by size. This realization transforms the ancient giants from sluggish relics to dynamic survivors,